this working. I'm going to try drawing on the computer, so it's, sort of need to see the screen and everything here. Let's see. I have my mouse pointer working. Yes, that's good. Then we're ready. The thought is today that we're going to use possibly not all 4 hours of the lectures that's set up, but at least we're going to try to design a more complex system. So the thought was the Mantis subsea saw that I designed with Imenco. We're going to do something similar to that, but not the same kind of system. Of course, that's Imenco's design, so we can copy that. But we're going to use some of the same principles that were used in that design, where we're going to use 2 hydraulic cylinders that are going to be clamping onto a pipe. So we need to calculate some pressures and stuff for that one in order to keep it in place. We're also going to calculate on a hydraulic motor that's going to run a saw blade. And we also need to calculate a hydraulic cylinder that is going to be feeding the motor and the saw blade forwards in a very slow pace so that we get the correct cutting speed for it. So in that order, I have opened up quite a lot of tabs up here with different reference points that we can go to as we continue along in our design. We can go in and check for what symbols to use and what kinds of data we need, so we can go in and get it. So hopefully I'll get the drawing done properly with this pen and everything, so we'll just try it. One more thing is that for the first break, we're going to break a little bit before 9, and I'm probably not back here until a little bit past or quarter past, so closer to 20 past or something. That's because I'm having the first year Norwegian students into the machine lab to show them the Imenco equipment that's in there. That was the only thing that was fitting with their schedule, so I just have to do it right then. It just means that you get a little bit longer break, so we'll do a 20-minute break instead of a 50-minute break. Right. The first thing that we'll look at is, let's see, the first data sheet that I have up here, which is one that we've seen it before, the constructor ROV from Just Design. So we've actually looked a little bit at this from before. But my thought was that we are now going to get the information that we need about our hydraulic system, our hydraulic pump and flow rates and everything. We're going to get that from this ROV, because we're going to basically be designing this saw in order to be working with this particular ROV. So we need to figure out a little bit. And then we can see here on the second page, if we just scroll a little bit up and down here, we can see we have general stuff over here, mechanical capacity and interfaces. And here we have hydraulic capacity and interfaces. So it's this one we need to look at. So I'm going to zoom in a little bit so that it's a bit easier to see what we're looking at here. So we need to scroll over here and a little bit down. So we can see it has several valve packs. So I'll try to just mark the text there. So the first valve pack is 10 bidirectional valves with proportional flow control. So it means that we don't really need to put that much flow control into the system, because it can be run entirely through the proportional flow control of the ROV. So basically the ROV pilot has the ability of controlling the flow from the control container or the control room regarding whatever kind of vessel they're working on. But you can see here in the first valve pack, we only have 8 liters per minute as a maximum flow. And that is fair enough when we're running a cylinder. As you remember from last week, we had 10 liters per minute, and that was way more than what we needed for that cylinder. But running a motor usually needs quite a lot of flow rate. So in my experience, you usually need to think about at least 10 liters per minute, preferably 20, 30, 40 liters per minute, maybe even more than that. But we can see that it has several valve packs, so more of them. So it has a second one that is equal to the first one, but it also has a third one. So here we have 4 bidirectional valves with proportional flow and pressure control. So they are able to actually control the pressure also. So if we're not going to run at the operating pressure, they can actually lower the pressure coming out of these valve packs. And also with a maximum of 80 liters per minute for each of the 4 valves. So each of the valves can deliver 80 liters per minute. So there's quite a lot of flow rate for that one. So we know that if we connect at least our saw motor, so the hydraulic motor in our system, if we connect at least that one to valve pack number 3, we know that we can get at least up to 80 liters per minute for that one. So later on, as we are choosing a hydraulic motor, we are going to have to keep that in mind. We have a maximum of 80 liters per minute. It might be that we need less than that for our hydraulic motors, but at least we can't go over 80 liters because that's the maximum from the ROV. And most likely, we are not going to get fully 80 liters per minute because there is always some loss in the system somewhere. So that it would be nice to think 70, 75 would be our maximum for the hydraulic motor, just to be on the safe side that we know that the hydraulic system is capable of delivering enough. So if we continue on here a little bit, we see pressure and return manifolds mounted in the front of the ROV. That just basically tells us that our equipment needs to be connected to the front of the ROV. We are going to assume right now that our hydraulic equipment is going to be hardwired to the ROV. So we're not going to have any hot stab system or something that if we put in a hot stab system, that is going to restrict our flow quite a lot because of the valves going through the hot stabs and everything. So in order to simplify our system, we're just thinking that we are hardwiring it directly to the ROV right now. And it has one pilot-operated high-flow valve with a maximum flow of 160 liters per minute, and then another pilot-operated high-flow valve with a maximum flow of 250 liters per minute. So it's a pretty hefty hydraulic system built into this ROV. So we know, and this is the largest work ROV from Just Design. So it is a powerful unit. And we can also see the system capacity. It has 220 bar operating pressure and 160 liter per minute as its maximum there for the auxiliary system. So we're going to be assuming that we're connecting to the valve pack number 3 with regards to our hydraulic valve, our hydraulic motor. Our cylinders could be connected to valve pack number 3 also, but valve pack number 2 or 1 is not a problem either for the cylinders. They don't really need all that much flow rate. And we can see that we have the operating pressure of 220 bars. So we're going to have to think about either using 220 bars as our operating pressure, or we're going to have to specify that they have to use their pressure control in their proportional valves so that they're going to lower the pressure of the system. So ideally, our cylinders would work at 220 bars. What pressure our motor is going to work at, we're going to have to look at what motor we're choosing for it. But for the cylinders, it's usually easiest to just put them at the operating pressure because that's a lot easier. And if you start looking around, I could only find Norwegian sites for this, so I chose not to show it. But if you start looking around at cylinder suppliers, they usually deliver stainless steel cylinders and stuff with an operating pressure of 220 bars. So it's more or less like I'm not sure if it's a actual standard that says 220 bars in subsea systems, or if it's just that everyone has just agreed upon it, that 220 bars, that's a good number to use. So we use that in the HPUs, in the ROVs, and we use that in the equipment also. So it seems like, at least the impression I've gotten is that it's more of a common understanding that 220 bars is a fair operating pressure to use. So for the cylinders that we're going to use, we're just going to assume that we can get some that work at 220 bars. So that's going to be our operating pressure, and we're going to have to dimension it with regards to that. So I've put up one drawing here which I've named Hydraulic Schematic. I will be making these available for you after the lecture. And then I've made one which is the calculations, where I'm going to try to do some I'm going to try to handwrite some calculations in here. I'm not sure how well it responds to handwriting, but we'll just see how readable it's going to be as we go along. If it becomes completely awful on the screen, then I'm going to write it more cleanly before I make it available. So we've got the ROV set in place, and now I'm just going to start with the hydraulic schematic, and I'm just going to create a first very rough sketch of how our system is going to look like. So what we're thinking about is having a I need to do the freehand here. We're going to have a pipe in the middle. So I'm going to try to make it show like that. So this is the pipe that we intend to cut. So we're going to clamp 2 cylinders onto that pipe in order to stay there. And we don't have that much information available of how hard we're going to need to clamp onto the pipe right now, because what it needs to do, or at least what was our design principle in Amenco, was that it needs to be strong enough at least to hold the entire weight of the equipment while it was in air, so that the weight in air of the equipment, it had to be strong enough to hold that. So that if we were doing testing in a workshop, we could clamp it onto a pipe and we can remove anything underneath it, and it's going to stay there by itself so long as it has hydraulic power. So that is one possibility of doing it, but since we're not going to be designing everything around the hydraulic system, so the structure of it, we're not going to be able to know how much it's going to weigh. So we're just going to set a certain amount of pressure that we're going to put in here in order to hold it in place, just to simplify our system a little bit. So we have the pipe in the middle, and just to make it look a bit more understanding, we'll draw in 1 cylinder over here. You can see these freehand lines. It has a tendency to try to sort of smooth them out instead of making sharp corners, but we'll just have to make do with what we have. Most likely we would have to do some mechanical design and create some sort of claw on the end of the cylinder so that it fits the diameter of the pipe that we're going to clamp it to. And of course we will need one on the other side in order to clamp onto the pipe properly and keep it in place. These wouldn't necessarily have to be drawn as, even though I'm drawing them horizontally on the sides of the pipe, these could still be placed more vertically in our schematic, so that they were pushing upwards, but they could be using a lever system, and that the claws would be pushed towards, so that if the claw is placed like this and the cylinder is pushing on the outside of the claw, then we're basically using a lever system. It's rotating around the joint, and we're pushing the claw into the pipe. So then it's going to hold it. So that is one possibility of sort of making the whole equipment a lot slender, because if we're going to put them on the sides, this is going to be a huge piece of equipment that we're putting in there. But for the purposes of our hydraulic schematic, it's a bit more easy to understand it if we just put it in like this, because we don't have to draw in the claws and everything. So I'm going to do the connection points for the cylinders up top here. So just small connection points here. And we're going to do double acting cylinders for this one, because we want to be able to control the retraction of the cylinders. That also has a little bit to do with considering that this is going to go subsea, and it's most likely going to have a lot of buoyancy elements, so that it's going to be approximately neutral in water in order to make it a bit easier for the ROV to move it about. It also means that it's going to be very easy for the ROV to place it upside down and do a cut, or place it all the way around so that it's basically flipped with a bottom up, and it could be put in all kinds of situations when it's doing the cut. So we want double acting cylinders to make sure that we are going to be able to push the cylinders all the way back when we need to release it. So these are going to be connected. So I'll just push this one a little bit up here. Due to the drawing system here, I'm going to have to not use the dots when I'm connecting. I'm just using regular cross sections, which means that I'm going to do these bumps across when I'm passing over one line to the other. So now we've connected these. We're going to have to put in some valves and something to control them over here. And the thought is that I'm going to put in the motor and the valves in the middle, and then we'll put over on the side here, we'll put in the cylinder that's going to push the motor and the saw blade forwards. So for now, we're just looking at how we're going to build the hydraulic system. We're not looking that much at the data of what we need. So the exact size of these cylinders, we can decide that whenever we want to. The important part right now is to sort of figure out the layout of our system first off. So we're going to pull this one a little bit down here. I'm going to jump this one over again, just to get it down here. Now, if you remember when we have been talking about valves, we've been talking about slide valves and poppet valves. And the main characteristic of a poppet valve, the reason why we might want to use a poppet valve, is that once it's closed, it's leak-free. So it's not going to let any fluid pass it. Which means that if we pump fluid into the piston chamber of our two cylinders here and build up pressure, and we're clamping onto a pipe, if we have a poppet valve that's allowing this flow of fluid into the piston chambers, and we close that poppet valve, it's going to be leak-free afterwards, so that we are basically shutting everything in there. So we're not going to lose any of the pressure as we go along, which also means that we don't have to use the hydraulic pump as a constant refresher of hydraulic energy in here. So it is possible to shut off the entire system by using the poppet valve. And one way of using that poppet valve is, let's see, I'll just pull this one a bit over here to get a bit more room. The poppet valve would be a two-way poppet valve, so either closed or open. So if it's normally closed, we'll put in a spring system here so that it's going to jump back. I'm not sure if it actually manages to draw those. Might have to do them a bit larger. Yeah, larger springs for this system for drawing. And since we're subsea, we definitely want a solenoid system here. So we need to be able to control this in some manner. And then when we activate the solenoid, we're going to have a, let's see, it's going to be that one. We're going to have a flow coming through in one direction. Basically, we allow flow in both directions on this one. So I could actually put up both of those if we want it. So this is one way of ensuring that we're not going to lose our grip on the steel pipe that we're clamping onto. And that's very important when we're doing work like this, because as soon as the saw blade starts spinning and it starts cutting into the steel pipe, if we start losing our grip and we start sliding a little bit downwards, we're going to put a tremendous amount of force on the saw blade, and it's basically going to break everything. So we need to make sure that we stay in position when we've clamped in there. One thing we could do here is to add a check valve. For an example, on the outside here. Now it ended up with arrows. We didn't want that. Let's see. And just make a check valve here. This is going to be connected to this port. And this means that the check valve will open if we continue to add fluid from the pump. So if we continue to just push fluid towards it, the check valve is going to stay open, so we're going to keep the cylinders pushing against the steel pipe. But if we want to, we can shut off the flow, because that's going to, as soon as we shut off the flow, it's going to close the check valve, and it's also going to stop any leakage through the poppet valve. So that's an important thing we can put in here. Just set up a poppet valve. Handles handwriting fairly well here, so possibly the calculations will go well also. So we're going to be using a poppet valve on that one. We're now doing a more complex system than what is actually necessary. In a system like this, where we have an ROV, the ROV's pump is very flexible. It can handle quite a lot of strain. So most likely, we could have just let it continue pushing fluid into the cylinders and just keeping the pressure up by staying connected to the pump that way. That would most likely be enough. And I would also imagine that a company like Deep Ocean, for example, that's going to use equipment like this, they would prefer it that way. Because the less valves they have in their equipment, then the more easy it's going to be to maintain it. And also the more actions they can control through the proportional valves in the ROV. But we're not going to create this equipment. We're just doing this as a design exercise. So we can play with as much function as we want to when we're doing this. But it's important to keep that in mind. What kind of desires would your customers have for this equipment? Because you as a designer could sit there and this would be a nice feature, and this would be a nice feature, and this would make it even more safe. But it might be that the customer don't want those features. They want something simpler because they're going to use it, for an example, deep down in the ocean where it's difficult to control it. And the more features you add, then the more difficult it's going to be to control it. So they want it to be simple. But in order to put it out of context also, it would be possible to use this on land as a hydraulic saw also. So if we had it on land, we would have want to have all of these features in. So we're just going to pile on a lot of features just to check them out, how we can use them. Yeah. The check valve is so that we will allow flow into the piston chamber. If we continue to pump fluid in from the pump, then we're going to allow it to pass the poppet valve and keep on pushing on the cylinder. But as soon as we cut off the flow from the pump, then both the check valve and the poppet valve will be closed and nothing will pass through it. Yeah, basically so that it's not going to be necessary to open up the poppet valve in order to maintain pressure. So then if something should happen while you're down there, for an example, in the hydraulic coupling going into the cylinder, if that one starts springing a leak, so you have a leak of hydraulic fluid out there, then just trying to block out return flow, that's not going to be enough because you're going to be losing pressure through that hydraulic coupling. And that means that you would want to, in order to save the operation and finish it, you would want to be able to push in more fluid. Of course, in that situation, you might just want to activate your poppet valve. That would allow you to push in more fluid. But this can also allow you to, say you're having a really bad day and the poppet valve is also malfunctioning. That's going to allow you to maintain pressure for that moment. And if there is a leak and the poppet valve isn't working, you can maintain pressure until you're done with the cut itself and you have retracted your saw blade and everything is safe with that regards. And then you can just let the leak from the cylinder just continue until it loses grip on the pipe, and then you can release your equipment that way. So it's sort of this becomes a backup of a backup of a backup almost in the system here. So we're putting in quite a lot of function here in order to be able to to save our system if something should happen. But of course, it's not going to be enough just saying that we're going to allow flow in or restrict flow from coming out. So we're also going to have another valve down here. I lost my place there, but it seems like it picked it up again. This will be a regular directional valve. So we're going to have a 3-position directional valve down here. And it has a couple of ports. So we're going to add in the port that is going to release the cylinders here. And when this directional valve is in its mid position, we're going to have it closed. So these 2 ports are closed then. But down here we can have, if we want to, we can just run the pressure from the pump. So a P there and a T over here. So we can just run the pressure from the pump right in return to the tank in order to not strain our pump in that part of the circuit. If we push it over to this side, we will be retracting our cylinder. So let's see, put in an arrow there. And if we push it over to this side, we will be extending our cylinders so that we're going to push on our pipe. And this one also needs to be solenoid, so I need to remove that arrow point there. I'm going to have it solenoid controlled in both directions, like this. And we're going to put in spring return so that we get it set back in the middle. For some reason it doesn't want the springs if they're too small. There. So this means that now we have regular control, like we've looked at a regular system when we've been looking at different systems in our lectures. So we can activate this solenoid, and it's going to allow flow from P to, we put in A here, and we'll put in B over here. It's going to be very tight there on that one. It is possible to zoom on this one when you're looking at it later on, so it's going to be easier to read it then. So we have the A and B ports, where the B port goes up here, and it goes into the piston rod chambers of each cylinder. So if we allow pressure into the B port, we are going to be retracting the cylinders. They're going to be pulling their piston rods back in. And for the A port, it will bypass, if we allow pressure into the A port, it will bypass the check valve, and it will go up here and fill in the piston chambers. And most likely, a check valve like that usually has a flow restriction, and the check valve can be really small. We can have a really small check valve there, just allowing a small trickle of flow through, basically. And then when we want it to move quickly, we just open up the Poppet valve instead, because as soon as we activate the Poppet valve, we're going to have full flow going through the Poppet valve, and that's going to allow us full pressure on there. So the one down here would be a slide valve then. Just put this one in as a slide, just to differentiate them a little bit. So a slide valve there. And this one would be connected to the ROV. So I just need to put in a large triangle there. And this one is going directly back to tank. So I'll put in the tank symbol. The tank is, of course, the reservoir within the ROV. And the reservoir in the ROV acts as a compensator in itself. So that means that it's going to compensate all of the pressure here. But one thing that we need to think about here with regards to using this system is that if we activate this solenoid, allowing flow from our pump into our A-port and all the way into our pressure chambers. And we lock everything off, and we're clamped down on the steel pipe. But the part of the steel pipe that we're clamped down on is the part that we're going to remove after we've cut it. So what we do is that we don't release our pressure. We just cut, and then we basically use the saw as a handling tool to remove this piece of pipe. Maybe it's not that big of a piece that we're moving. So we're still gripping the piece of the pipe, and then we're lifting up our ROV and our equipment. The problem now is that we have 220 bars of differential pressure inside the piston chamber of our cylinders, while we're down at, for an example, 3,000 meters. But then when we're pulling it up, the differential pressure is going to increase as the external pressure, the hydrostatic pressure outside, decreases. The pressure inside is not going to decrease. So that means that our differential pressure is going to be increasing as we pull it up. So the cylinders that were supposed to be able to handle 220 bars, they were designed for that, so that shouldn't be a problem. They might suddenly be up to 500 and something bars, because they've added 300 bars by just lifting it up to the vessel. And then you suddenly have, if they haven't been broken by then and burst open, basically, or the couplings have gone bad and just popped open or something like that, if none of that has happened, when they get it up on the pressure vessel, you basically have a ticking time bomb on the deck of your ship. Because sooner or later, that high pressure in there, that's going to just burst out. And as if you can remember when they did the pressure test on that hose, you could see at 1700 bars, it just burst completely. It was basically an explosion. So if you get something like that happening, and this is made of steel also, it's not a hose that's inside a pressure chamber that's supposed to be able to handle it. It would be out and about on the deck. People will be walking around it, and it can just burst anytime. So that's really dangerous. So that's one of the reasons why I would bet that a company like Deep Ocean, they didn't want this possibility of locking the pressure in there. From the perspective of an engineer and the technician that's doing the cut itself, the cutting operation itself, they would really want that there, because they would want to make sure that this cut can't be interfered with in any way. But from the operators of the vessel and everything, they really don't want a bad situation like that to happen, because if someone is basically not doing their job and not paying attention, they can bring a bomb up to the ship that way. But for our system, we're now going to focus on the cutting situation and creating a nice piece of hydraulic equipment. So we're going to leave it in there. That's the part of our hydraulic systems lecture. The warnings about deep ocean and everything, that's more for the subsea technology that we're looking at. So now we've figured out a way how we can control our cylinders. So later on, we're going to calculate a little bit on the cylinders just to see that we can get the correct amount of pressure and force from them. So now it would be nice to start looking at the hydraulic motor. We'll start by just drawing in a couple of symbols, and then we'll start the break a little bit before 9 and have a 20-minute break. But first off, we'll just draw in the symbols. So the symbol for the motor looks exactly like the symbol for, not exactly, but almost like the symbol for a pump, where we have the circle. But with a pump, you have a black triangle inside that's pointing outwards. And with the motor, you have a black triangle that's pointing towards the center instead. So depending on if you have a motor that can be run in both directions, you would have two triangles, both of them pointing into the center, so one on each side. If it was a pump that could pump in both directions, it would have two triangles, each of them pointing outwards. So that's the main difference for these two. So for us now, with a saw blade, a circular saw blade, especially if we're using a one with teeth, then we're going to have to only run it in one direction. Because if we run it in the other direction, we're just going to be destroying the teeth of the blade. If we're cutting with a diamond cutting disc or something like that, or a fiberglass cutting disc, anything like that, kind of equipment that you would use with a grinder in order to cut, then we can spin it in whatever direction we want, because that one can cut either way. But with this one, we're going to use a toothed blade, so that we need to spin it in one direction. And that would mean that design-wise, it would be wise for us to choose a motor that can only run in one direction. Because then we are sort of, the only way that we're going to destroy the saw blade then is if the technicians that are assembling it are putting the saw blade on the wrong way around. So they basically just flipped it when they put it on. So it's going to rotate in the wrong direction. So we're going to use one that's only going to go in one direction. And I don't think I can fill in, no, I can't fill in with black in there, but it's supposed to be black, that one. So I think I can put a triangle in there afterwards. But we'll do a break now before we continue on, and we'll be back in 20 minutes and continue on. If you can use the what? Oh yeah. Usually you can do that, yes, adjust the spring. For a poppet valve like this that is either going to be open or closed, it's not really necessary for it. That's more like for the pressure relief valves that have a pilot pressure and are going to open up at a specific pressure, so that if you want to change that pressure, you change the rate of how much the spring has been compressed beforehand, basically. Because then you make it more, you need more force to compress the spring further then. That's the main point of having adjustable springs for them. So for this poppet valve, it wouldn't be all that purposeful to have an adjustable spring there. It wouldn't be a problem having it there at all, but it wouldn't really make a difference for the function of the valve. So the only thing it would do was that you probably would use a little bit more electric current in order to push it in if you set it a bit harder. So we were talking about the hydraulic motor. I'm going to see if I can delete that one, and let's see. It's possible to do some shapes in here also. See if I can rotate this one 90 degrees. And that one I can make black at least. Then it looks a bit more like the proper symbol for it. So for the hydraulic motor, we're going to have I'll just draw it out on top here. There is, of course, a shaft coming out of the hydraulic motor that's going to be connected to the saw blade itself. I'm not going to draw in the saw blade or anything here, because that's a whole sort of calculation in itself, starting to look at the saw blade and how many teeth do we have on a saw blade, how much cutting speed do we need, and all of this. It's going to be basically back to the materials course that you did with when you had the welding lab and everything like that. It's more related to that course and not to this one. But if you were designing something like this, you would of course have to do that part, because you would have to figure out exactly how fast is this hydraulic motor needed to run. So how many RPMs do we need to get from this hydraulic motor in order to get the correct cutting speed from our saw? So that would have been something to calculate there, but since we're focusing on hydraulics now, we'll leave that be for now at least. So the hydraulic motor, we already know that on the ROV we had proportional valves, so that we could regulate the flow that we are getting in. But let us say that this might be an equipment that's going to be used on a different ROV that might not have flow control on the valves. So we might want to have our own flow control valve in here, just to be on the safe side. Usually, if you're designing something, you want to design it to be sort of all-purpose, so that it's not going to be restricted to working with just that ROV or something that is completely equivalent to that ROV. You want it to be most work ROVs be able to use this equipment. And quite a lot of more simple work ROVs have much less equipment than this constructor one from Just Design. So they're really simple compared to it in that regard. So we would want a flow control valve in here, just to be able to control it. If you were going to use this with the constructor ROV, then of course you could just open that flow control valve to maximum, and it's not going to be a problem, because then you just lock it open at maximum, and you're not going to use it when you're using it with the constructor one. You're going to use the built-in flow control instead from the ROV. And then if you switch it over to a more simple work ROV, then you have the possibility of starting to fix it here. So for flow control, we have the two throttle points there. We have an arrow going past them, and that arrow needs a point. And we also have, let's see. No, I'm switching on that one. That wasn't the purpose. do another arrow over here. Now I need to switch it. Because it's going to be able to send off whatever flow is too much. So if the constructor ROV couldn't regulate its flow, it would be sending out 80 liters per minute straight off to this one. And if we wanted 60 liters per minute on our hydraulic motor, then we would need to have 20 liters a minute return to our reservoir. So then we would want it to be like this, that we have a return to tank option up here. But let's see, we are not going to have arrows on those. Let's see. Just remove the arrows. There. But of course also, it might be that we're going to cut something else, or maybe we're switching a blade to another blade, so we need a different cutting speed. And that means that we want this one to be variable. So we want to be able to control it. So we'll set, that was on the wrong end. So we'll set a variable symbol across it so that we know that this is something that we can regulate on this one. One thing to keep in mind there is that on most valves like that, the regulation is manual. So you have to preset it before you start your operation. So on deck on the vessel, you're going to have to run your blade, and you're going to have to use some sort of measuring device to figure out exactly how fast the saw blade is rotating. And then you sort of turn it manually until you get the correct speed for it. So you have to preset it before the operation starts. There are some that are electronically controlled, but those are really expensive, so it wouldn't be... this is already going to be a pretty expensive equipment, considering all of the functions that we're putting into it. Every valve you put into a piece of equipment like this is going to make it more expensive. So putting in electrical control would be way over the top for this one. So then we need to continue on to the next parts here in our design. So we'll continue. I'll remove that one. Let's see. We'll connect it to a pressure reducing valve, just in case we're using it on a more simple ROV. We want to be sure that we have the correct pressure entering it. Because, yes? That one is, it connects to, I'm not quite sure why they have it like this. I would have put this one, I would have put the tank symbol down here, just logically. But for some reason, they make the symbol like this. And I'm thinking that maybe it has something to do with the internal movement, that there is something that's, it's basically sliding up here, and then it's opening up. So that if you get too much flow, it's going to push the slide valve over here, and then it's going to open up. That's what I think is the reason behind it, but I'm not quite sure why they put it like that. But that is the official symbol for it. So that's why I draw it like that. But to be completely honest, I would have had it like this, drawn in. That's where it's going to return to tank. But for some reason it's up there. And exactly why, I really don't know. But for the way that this valve is built is that it's usually two valves that are built together, so that you have one throttle valve that's regulating the flow, and then you have one more of a sort of like a pressure reducing valve, basically. Works on the same principle. That's going to open up when the pressure and the flow rate becomes too high, so it opens up the tank. So that's why I'm like with this one, when you activate the solenoid, you are pushing this slide over here so that you get contact between them. I think that is sort of what they're thinking about here, that you're sort of pushing the arrow up there when it's going to release the tank. But yeah, it's a bit difficult to handle sometimes how they put these up logically. It's probably a pretty good logical explanation once you get it explained to someone who knows exactly why it's like that. But it's a bit difficult to see sometimes. Before the flow control, we have a pressure reducing valve. So we'll do freehand there and up to there with an arrow. And a flow control like that is pilot operated, and it's pilot operated after the fluid leaves the valve. So, or as the fluid leaves the valve, rather. So on the outlet port, it has this connection that goes over here, back here, and that is a dotted line because it's a pilot port that's going in there. And if the pressure becomes too much on this side, it's going to push this arrow over to the side, and then we're going to have contact with the tank there, so connection to the tank. And this one also goes from this end over here for some reason. I would have had it over here and up like that, but again, it's not always all that logical why they put their symbols in like this. So we have pressure here on this side, and we have an A port on this side. Basically the same on that one. It's going to be a bit tight up here, so I'm not going to put it in. But we also want to be able to control our hydraulic valve. So we need to be able to say that now you're going to spin and now you're not going to spin. So we need to have some sort of control valve for it. And to do that, we could put in a let's see, one like this, a two-way valve. And of course, we'll have that one solenoid controlled because we don't have a diver down there that can actually push a button or anything like that. So we need to have it controlled in some other way. And this one is going to be, oh, it doesn't want to draw there. Let's see. Oh, I'm missing it. Missing the point where it's supposed to be. Let's see. Over here. So this one is going to be closed when it's not in use. So when we don't want the motor to run, it's going to be closed. And then we'll have it being open when we activate it. Let's see. Arrow in there, and we'll have closed return to tank. I think I'm out of bounds here, basically. Let's see if I can extend this one a little bit. Isn't that possible? No, I can't extend it. Let's see if I can lift it up a bit. That should work. Like that. Then I have enough room to put in the rest here. Because like on this side, we're going to connect the pump to this one. I'm just going to create a triangle there, and then we have to tank on this side. Looks like a U instead, but but there are a couple of things that we haven't looked at yet with our motor. Of course, we're going to have to return. Yeah. Yeah, I'll try to zoom in a bit so that we can see it a bit more clearly. That was maybe a bit too much. So let's see. Zoom. And just move it over here. So we have the pressure reducing valve up here, where we have the pressure coming in. And if we get too high of a pressure, the pilot pressure is going to push the slide over and return to tank until the pressure is down to what it's supposed to be. But before that, we also need to say that when are we going to allow flow to go through our hydraulic motor? So then we have this two-way directional control valve, where we have 3 ports. So we have 1 port going into the hydraulic motor side of the system, and then we have 1 port going to tank, and 1 port that is connected to the pump system. When this one is closed, it's going directly from the pump and directly back to the tank, so that there is no resistance to the pump. It's just pushing the fluid around, basically. And the port going up to the motor, that's closed. But when we activate this one, it's going to push this over, so the closed part will be back to tank. That one will be closed. There will be no return to tank through this valve, and it will be getting pressure from the pump and all the way up to the hydraulic motor through everything else. But then it's getting the full operational pressure of the system. And I've forgotten to put in a spring at the end there, just to show that we can control this one. I'm going to create a better drawing afterwards, I think, just to get to show it a bit better. So I'll just zoom out here. So now we need to know, we figured out how we're going to control our flow by using a directional control valve down here. We've also figured out how to control the pressure if we can't do it from the ROV. And we've also figured out how to control the flow if we can't control it from the ROV either. So these two would basically be just set to a maximum if we maximum position, maximum flow going through, and maximum pressure going through. If we are using the constructor ROV, that can regulate everything itself. And if we are using a more simple ROV, then we can preset everything beforehand. So what's going to happen is we get the flow through all of this. It's going into the motor. It's going to spin the motor at the correct rotational speed. And we are going to get flow that is going back to the tank from the motor. But there is one more thing that happens when we have a hydraulic motor, and that is that there is always leakage inside the hydraulic motor. And since there is always leakage in a hydraulic motor, it means that that leakage oil, it has to go somewhere. And where it goes is actually along the shaft to a chamber outside here. And that's really not good with regards to us putting this deep underwater and having a lot of pressure on the outside, because between the shaft and the housing of the motor, there is just a regular sealing. And if you have leakage oil on the inside of the sealing, and you have high hydrostatic pressure from the seawater on the outside, it's just going to basically push that sealing straight in, because the leakage oil has no pressure. So it's basically at atmospheric pressure when it comes out there. So it doesn't have any of the operational pressure or anything like that. So what you have to do is connect this leakage oil. So I'm going to create a line. I'll just connect it to the shaft portion here. And a bit over there. And the leakage oil is usually shown just as a pilot line. So it's shown with a dashed line as the line symbol for it. But this one has to be connected to its own, let's see, just start a new line here. It has to be connected to its own compensator. So for the rest of the system, it is compensated by the compensators in the ROV, because the whole reservoir is compensated. But this leakage oil is unable to return to that reservoir because it has no pressure and the reservoir is under high pressure. So what we need to do is to have a compensator in here, and then we need to put the leakage oil down from there, let's see, out of the compensator, and into the tank. Preferably, we would also have a, let's see, I can draw that in actually. We would also have a check valve here, so that we would only allow high enough pressures to return to the tank. So dashed line there again, and I'll make the tank symbol here. So what happens here is the compensator can be drawn in like this, basically looking more or less like a cylinder, only it only has a piston, it has no piston rod. And that's the basic function of it also, because you get water pressure, hydrostatic pressure from the outside here, pushing on the piston, and it's creating pressure on the inside. So you're equalizing the pressures. So the pressure in your compensator system here is going to be equal to the hydrostatic pressure. So then that way you have managed to equalize this and gotten a high enough pressure in the leakage line so that it can actually return to the tank. And you're not going to have the compensated pressure from the tank going the wrong way around and sort of messing up your hydraulic motor here. So then the last part of our schematic itself is to put in the cylinder that's going to be pushing the hydraulic motor and the saw blade itself forwards. So this cylinder would basically be pushing from the structure and onto some sort of platform that's on a rail system or something like that, where the hydraulic motor is placed along with the saw blade attached to its shaft, so that you will basically be pushing that entire platform forwards. So in order to draw that, we'll just do a vertical cylinder here, just to show that we're pushing in the same direction as the motor is supposed to move. And we'll have, let's see, take it out from this side. We're going to have to really throttle down the flow of this one. So we're going to have a the same type of flow control valve as we have over here, but it's going to be a completely different range, because the flow control valve we have over here is most likely going to be a range where it's going to allow quite a lot of flow through. So 50, 60, 70 liters per minute maybe. That's what it's going to allow through. But the one we have over here, it's only going to allow a very small portion. It's basically almost going to block the flow. So it's just allowing a small trickle of flow through it. So it's a completely different range. So even though it's the same principle of valve, it's a completely different valve for it. So I'll put it underneath here and connect it. So it's the same symbol that we used on the previous one. And it's of course going to be adjustable on this one also. And again with the symbol where it's a bit of a silly placement for the tank symbol, but I'll just have to cope with it. And then we have the arrow down here. And one thing that we want to be able to do here is that when we are going to retract it, we want full flow through it. So we don't want to restrict the flow when we're going to pull the cylinder back. So that means that we are also going to have to connect it to a check valve on this side. because then when we are putting pressure into the piston rod side, we allow full flow past the flow control valve, so it's not going to restrict anything in that case. So that might be very important, especially if we have slightly jammed our blade in there. So if our claw cylinders have been slightly losing their grip a little bit, maybe there's been some vibrations and shaking, so that they maybe just sort of slipped down for a millimeter, maybe not even more, but it might be just enough that you've gotten a slight angle on your saw blade and it's just slightly jammed in there. And then you would want full flow and pressure coming into the cylinder in order to just be able to yank the saw blade back, so that that's a possibility to do. Oops, I switched the tab there. Let's see. So this one also needs a directional control valve, but for this one we're going to use a two-way one. Where we put flow going to the piston rod side as the default option. So that it's always going to push this cylinder backwards if we release control of it. So we'll connect this one. And then we have return to tank over here. And we have a connection to a pump over here. Again, we're going to need a solenoid control of this one, and we're going to need a spring return to the original position. So by using this one here, we're getting a full pressure back, and we're just basically, so long as the system is running, it's making sure that we definitely have our cylinder pulled all the way back. The reason for doing this instead of just blocking off this one, using basically one like this, is that once you are lifting this equipment back and forth, you have quite a lot of weight in the motor and this platform and the saw blade, and that could start pulling on the cylinder. So it would be nice to just run the system all the while and just make sure that it stays all the way back, so that the saw blade doesn't inch forward a little bit, because then it's going to come into conflict with wherever it is you're going to try to place it. So usually, once you've clamped down between a saw blade and whatever it is that you're going to cut, there's usually going to be, we're talking maybe 10-20 millimeters between there, so it's not a lot that the saw blade has to be jerked forwards before it's going to start to come into contact with whatever it is. And you really don't want to start a cutting operation with your cutting tool already in contact with what it is that you're going to cut. That's going to be a bad situation. So you want to avoid that. So that's why we keep this one putting full pressure on the cylinder and just pulling it back at all times. So then we have a fairly complete system here. It might very well be that we need to do changes to the system as we go along and do calculations and start looking at stuff, but we've got sort of a mental picture of what our system is going to do and how it's going to do it. So we need to start looking at different stuff here. So I think the first thing we'll start looking at is the motor itself. So we'll start doing the calculations for the motor. And for this motor, we're just going to use, let's see, that one, Danfoss, that has quite a lot of different hydraulic motors. And we're just going to use basically just whatever we can find here. I think it was on page 20 on this catalog. Yes, around page 20 we have the very first hydraulic motor that we find, I'm just going to zoom it in and put it up fully here. Let's see, 20. Zoom out one bit. Didn't want to. Let's try with the mouse instead. Let's see. Quite see why I didn't want to show the entire part there, but okay, so that's it. There, that's a bit better. The control button was locked in on this one. I'll basically zoom in a little bit more, so I'll have to scroll a little bit while we're looking at it, but that we'll just have to do. We can start looking at a hydraulic motor before we have a break. So, what happened now? We have it. So we did look a little bit at this when we're talking about hydraulic motors, and you even saw it in the lab that you had, because it was a Danfoss motor that you had there. This sort of schematic might look a little bit different if you're working with another supplier, but it's basically going to look pretty much the same. It's going to give you the same kind of information. It might not be using red and blue as illustrations for good working areas. In this case, it's showing where it's blue, no, where it's red, in the red areas here. The hydraulic motor can work within those areas, but it should only work intermittently, so only in short bursts in those areas. So with regards to pressure, we can see that a pressure above 100 bars and up to 140 bars, it can work with that kind of pressure, but only for a very short while. So that means that, for example, if you have 100 bars as your operating pressure, and you're running at that, and you get a pressure peak of 120 bars for just a little while, half a minute or something like that, it's not going to damage your motor. It's going to be able to handle that pressure peak, because it can work under that condition. So, and also if your system is based on the fact that the hydraulic motor is only going to work for 10, 15, 20 seconds at a time, you could actually design a system that is working at 130, 140 bars with this motor, because by using that, you're using it for a short enough time period that it's not going to damage it. The same goes over here with rotational speed. We have the rotational speed down here. We see we have per minute, it says there, so it's rotations per minute. And if we pass 1600 or 15 to 1600, depending on how much pressure we have, then it's only going to work for a little while under those conditions. The thing is that when you're doing cutting operations, you usually want a pretty high speed. The positive side is that we're cutting steel, so steel pipes is what we're aiming to cut, and those are usually require slower cutting speeds than, for an example, wood or anything like that. Wood or plastics, they require very high cutting speeds for cutting it, while steel is a lot less, so we probably won't need to be thinking about anything up in this range over here. So we could stay down at 800 to 1200 RPMs, most likely. It also depends a bit on, of course, the diameter of the saw blade that we're going to use. the larger the diameter, then the more rotational speed we're going to need in order to gain enough circumferential speed for the teeth. Another thing that we need to look at is the efficiency. So we can see here we have an eta of 73%, and that is this part that's going all the way around here. So it's basically sort of a very elongated ellipse in this case. And within that, you're going to have at least 73% efficiency from your hydraulic motor. And then you have 65%, so that's a bit larger. You have a larger area here, and then you have the last one, which is 50%. So if you start moving down here, very low pressure, very high speed, you don't really have that much efficiency. You have less than 50% efficiency on your hydraulic motor. You can also see here we have how many kilowatts we're running. They've even put it in horsepower in case you want to be calculating with horsepower instead. Most industries are moving over to using kilowatts anyway, so I would highly recommend that you don't learn how to do stuff in horsepowers because it's being phased out. Even car manufacturers have started using kilowatts instead of horsepowers. Now, they still usually have horsepowers on their data sheets, but they highlight the kilowatts, and then they have the horsepower in parentheses behind it, so the equivalent. So I think it's only a matter of a couple of years before they start dropping the horsepower altogether. Yeah, I think we'll do a 15-minute break before we continue on with this one. Yeah? Yeah, I can turn it back to it.